say, well, you can authenticate in a regular way, or for not much higher price, you can run all your authentication protocols at this affiliation-hiding anonymous, in this anonymous mode, okay? So this is actually what I just said. We will relax the problem at first, okay? And this is a paper from last year, where we will allow the resulting protocol to be linkable. Namely, each party will have a random string, like Alice will have a string A, Bob string B, and these are random pseudonyms, okay? So they cannot be, they don't look like CIA pseudonyms or FBI pseudonyms or Purdue University pseudonyms. They are random numbers. On the other hand, everybody just has one number, and therefore it's linkable because occurrence of the same person, even though nobody learns what institution they're affiliated with and what policy they have, nevertheless, two occurrences of the same person are detected, okay? Which, is not fully satisfactory for somebody who wants perfect anonymity, okay? Because you can derive some properties from the fact that you see the same person in two different places, and you're like, aha, he looks like an FBI guy. Okay. Okay. So we allow at the beginning for the two parties to exchange these pseudonymous random numbers. Okay. And then the secret handshake protocol proceeds on the following input. So policy is just a public key, like a public key of the certification authority. Okay, and the ticket is essentially a signature of the authority on this pseudonym. You can ask, why did I make it so particular? Why do I ask for these things to be signatures? Later on in the talk, you will see that this notion, however you define it, actually implies signatures. So you can just as well call these tickets signatures because they must satisfy security properties of a signature scheme if they want to be secret handshakes, okay? So we can just as well call them signatures to start with. Another thing these are signatures, but also we can call them trapdoors for a given ID. So here, ID, I will call these pseudonymous random strings, I will call them IDs. And the signatures I will call trapdoors. Also, I will allow, so once I have a system like this, I have a revocation in an easy way. I can support revocation easily by just, if some IDs are revoked by a given CA, the list of these IDs is published, okay? So, and now it's up to the encryptor or up to the party who wants to authenticate people, whether or not somebody is still affiliated with CA2 to check this revocation list. So therefore, we assume that that CA2 includes the revocation list. Okay. So it's okay. So how do you revoke? So how do you do this? So since identities are exchanged, I just check whether A is not on the revocation list, and that's it. And from that point, I can forget about this revocation list. Okay, so the problem was actually posed not by us. At first, this type of secrecy in the authentication was considered by Martin Abadi, but it was done for symmetric key authentication, not for public key. And for symmetric keys, it's significantly simpler. And then the notion of secret handshakes was introduced, at Oakland by Alphonse et al., a bunch of researchers from Xerox PARC. And it was solved by using bilinear Diffie-Hellman, okay, which means using bilinear maps. Essentially, as you will see in a second, identity-based encryption done via bilinear maps implies this notion in a very simple way. That's what these guys did. What we do is we notice that you don't need identity-based encryption. What you need is an affiliation-hiding, a more general concept encryption. And in particular, we do this affiliation-hiding encryption from computational Diffie-Hellman without bilinear maps, which has two consequences. It's a weaker assumption, it's a more standard assumption, and it uses any discrete log, so it uses regular modular fields, not elliptic curves, so it is much faster. Okay, so actually our protocol is quite simple, and this is it. So what you the secret handshake proceeds as follows. It could be reversed, but we chose this to present it this way. It doesn't matter which way it's drawn. Alice encrypts her proof of possession of her ticket. Okay. She encrypts it under a key that is derived from Bob's pseudonym and the certification agency that is in Alice's policy. Okay. Now, this scheme, first of all, like the way it should work is that the only way that you can decrypt this encrypted statement is so the way this public key is formed, in other words, is that the corresponding decryption key that corresponds to this encryption key is a signature on string B issued by certification authority CA2. Okay? In other words, we need an encryption scheme for which signatures are decryption keys. Okay? So if you think of a trapdoor as a signature by the authority on the pseudonym, then I need a signature scheme such that if I see the message that was signed, and I know, or I assume, or guess, the public key that signed that message, from these two elements, I can form an encryption key for which the signature is the corresponding decryption key. Okay, and for bilinear maps, that thing can be non-interactive. For El Gamal and things that we built it on, computational Diffie-Hellman, we will only get an interactive encryption to achieve this. Now, of course, interaction is worse than a lack of interaction, but this interaction is only two rounds, so it's only boom, boom. And because there is an exchange of identifiers, the first round of this interaction can be piggybacked on the exchange, and therefore our round complexity doesn't grow. So we have the same number of rounds as they do. Even though the tool we use is an interactive encryption scheme. Okay, so now what do we need of this encryption for this protocol to be a secret handshake? In other words, for this protocol to hide the affiliation, as I said before, these two secrecy properties I wanted. Okay, so simply speaking, the encryption must hide this certification that either party assumes. Okay, so the certification authority that signed either party's ticket. So it's that